Representations of functions as power series. In this section, we're going to see how we can take a basic function and transform it using power series. And then we're also going to see how differentiation and integration affect a power series. Recall from a previous section, we learned that sigma n equals 0 to infinity of x to the n, which was 1 plus x squared plus x cubed, etc., was equivalent to 1 over 1 minus x for absolute x is less than 1. So then the power series representation of the function 1 over 1 minus x is f of x is sigma n equals 0 to infinity of x to the n. So we can treat this as a basic function and try to transform it if we're asked to find power series representations of other functions. Let's see several examples of that. Find a power series representation for the function and determine the interval of convergence. Alright, so I've got the function is f of x is 5 over 1 minus 4x squared. So notice that this is fairly close to 1 over 1 minus x. Alright, that's what I've got to keep in mind. Alright, that 1 over 1 minus x is the same as sigma n equals 0 to infinity of x to the n. Keep that in mind. So I'm trying to make my new function look sort of like that. And so here's what I'll notice. I can think of this as 5 times 1 over 1 minus, and I put the 4x squared in parentheses just to kind of set it off. So notice I have that 1 over 1 minus a quantity. And I'm just multiplying the whole thing by 5. So that means that my function f of x can be written as 5 times sigma n equals 0 to infinity, and instead of x, 4x squared to the n. Now I can bring that 5 inside if I'd like, if I want to just write, I can write it like that if I want to. What's the interval of convergence? Alright, well, instead of an x, I have a 4x squared. So instead of, for the basic one, we had absolute x is less than 1, so now I'd have absolute 4x squared is less than 1. Now let's see, 4 is positive and x squared is never negative, so I really don't need any absolute here. So where is 4x squared less than 1? Well, that implies that x squared is less than a fourth, and solving this using techniques we've learned in an algebra course, that's the same as writing negative 1/2 is less than x is less than 1/2, which implies that my interval of convergence is negative 1/2 to positive 1/2. So here's another example. Here our function is given as 1 over x plus 10. And again, if we're trying to relate this to 1 over 1 minus x, well, this is a little tougher. I don't have a 1 in the denominator, and I don't even have a subtraction in the denominator. So I've got to play around with this a little bit. I've got to use some fancy algebra tricks here. First thing I'm going to do is I'm going to take the denominator, I'm going to factor a 10 out of it. So I can write this as 10 times, I can write the denominator as 10 times, and I'm going to switch the order of the terms here, 1 plus x over 10. I factored out the 10, so now at least I have a 1 in the denominator. Now, I need a subtraction, not an addition. So I've got 1 over 10 times 1 minus negative x over 10. Addition, subtraction of a negative. So, and then I can write this as 1/10 times 1 over 1 minus negative x over 10. And so now I've got it as a transformation of that basic function. So the function 1 over x plus 10 can be written as 1/10 sigma n equals 0 to infinity negative x over 10 to the nth power. I could bring the 1/10 inside again if I'd like, but it's not necessary. Let's determine the interval of convergence. So I'd need absolute of negative x over 10 to be less than 1. So now I've got that x, that's an odd power on the x, so I need the absolute still. So, and the absolute value of the negative goes away, so absolute x over 10 is less than 1, which means absolute x is less than 10. So my radius of convergence, no, I'm sorry, I've asked for the interval of convergence. So that's the same as negative 10 is less than x is less than 10, and my interval of convergence is negative 10 to 10. All right, here's a third example. Now our function is x over 2x squared plus 1. So now would be a good time to try this one out on your own and see if you can come up with the power series representation for the function. So I'm trying to compare this to 1 over 1 minus x. I've got that x in the numerator, and I can use the same trick as in the previous exercise to write that 2x squared plus 1 as 1 minus a quantity. So I can write this as x times 1 over 1 minus negative 2x squared. So that means I can write the function as x times sigma 0 to infinity negative 2x squared to the n. Now, I can bring this x inside carefully and combine it with the other x. But before I do that, let's figure out the interval of convergence. So I would need absolute of negative 2x squared to be less than 1. So that's equivalent to 2x squared is less than 1. So then x squared is less than a half, which is negative 1 over root 2 is less than x is less than 1 over root 2. So I'll write the interval of convergence rationalizing the denominators as negative root 2 over 2, comma root 2 over 2. Now let's go back and show how I can carefully combine this. So I can write this as x sigma, I'd have a negative 2 to the n, and I'd have an x squared to the n, that's an x to the 2n. So now if I bring this x inside, multiplying by x, right, so if I remove it from the outside, bring it inside the sigma, I can write the function then as sigma 0 to infinity, negative 2 to the n, x to the 2n plus 1. There will be times where we will need to differentiate or integrate a power series. And turns out that if we have a power series with radius of convergence r, then for the function represented by that power series, the derivative of the function is equivalent to the derivative of the power series, and it will have the same radius of convergence r. Similarly, the integral of the function is equivalent to the integral of the representative power series and also has the same radius of convergence r. So basically, this allows us to integrate or differentiate power series representations of functions. So for example, what if we needed to express 1 over 1 minus x quantity square as a power series? So I can't use the same just basic transformations on this one as I've done with the previous exercises. So instead, we have to use a little bit of ingenuity here, and we might notice that the derivative of 1 over 1 minus x, remember that's the same as 1 minus x, that's 1 minus x to the negative first power. So that would then become negative 1 times 1 minus x to the negative second power, and then from the chain rule, I'd have another negative 1. And so that's 1 over 1 minus the quantity 1 minus x squared. So 1 over 1 minus x squared is the derivative with respect to x of 1 over 1 minus x. Well, that's the same as the derivative with respect to x of sigma x to the n from 0 to infinity. So now, just applying the power rule for derivatives, I should have a sigma, and I'll have an n, and an x to the n minus 1. But now be careful here, because if we look at this exponent, this n minus 1, we can't start with n equals 0, because then that would give me an x to the negative first power. So we would generally have this then start at n equals 1. Now, we like to start at, we like our sigma to start at n equals 0 in these situations. So I will decrease this n, and I will increase all of the other n's on the inside to match that. And so I can write sigma n equals 0 to infinity of n plus 1 x to the n. And there's a representation of 1 over 1 minus x squared. So there is one approach, just sticking with the sigma notation and sort of playing with the index. Another approach is to, from this point, if we want we know it's d by dx of sigma x to the n, so that would be d by dx of 1 plus x squared plus x cubed plus dot dot dot. And so then that would be equivalent to 0 plus 1 plus 2x plus 3x squared, and I'll list one more term of 4x cubed plus dot dot dot. And now from here, write the sigma notation. Sigma n equals 0 to infinity. I know I have an x to the n, and I need a 1, then a 2, then a 3, but I'm starting at n equals 0, so that's n plus 1. So either approach works, just whichever you prefer to work with. Express the natural log of x plus 10 as a power series. Well, I notice, again, you have to sort of notice something. I notice that the natural log of x plus 10 is equal to the integral of 1 over x plus 10 dx. So we won't worry about the absolute value here. So then the natural log of x plus 10 is equal to the integral of 1/10 sigma n equals 0 to infinity of negative x over 10 to the n dx, where we figured that out in a previous exercise. Right, that was the power series representation of 1 over x plus 10 we figured out. Now, with when finding integrals, when finding an antiderivative, it's usually easier to work with the expanded form of the series. So this is then equal to integral 1/10, and now I'll expand the series. This would be what? 1 minus x over 10 plus x squared over 100 minus x cubed over 1000, etc. dx. Now I'll integrate. All right, I'll find the antiderivatives. So I'll have 1/10, because that's a constant multiple or multiplier. The antiderivative of 1 is x, minus the antiderivative of x, that's x squared over 2, so I've got an x squared over 2 times 10, plus, similarly, an x cubed over 3 times 100, minus an x to the 4th over 4 times 1000, etc. And I'll have a constant from the integration. Now let me bring that 1/10 inside. Let me go ahead and distribute. So I'd have an x over 10 minus an x squared over 2 times 100 plus an x cubed over 3 times 1000 minus an x to the 4th over 4 times 10,000 ... and again plus a constant. I guess I really don't need the bracket here. Now what's the constant? How can we figure that out? Now let's do a little bit of side work here to figure out the constant. So what I'm going to do is I'm going to make a substitution, because remember the left-hand side of this is the natural log of x plus 10. So I'm going to make a substitution and try to solve for c. Now look at all those terms on the right-hand side. All those terms on the right-hand side, except for the constant itself, have an x to a power. And so I'm going to wipe them all out. I'm going to let x equal 0. By letting x equal 0, the left-hand side becomes the natural log of 10, and the right-hand side becomes a whole bunch of zeros plus c. And so then c is equal to the natural log of 10. So the natural log of x plus 10 is equal to, I'm going to write a sigma notation here, so sigma n equals 0 to infinity, and I've got to figure out what goes on the inside. Well, I see that it's an alternating series and it's starting with a positive, so I'll use negative 1 to the n minus 1 times. Now let's figure out everything else. Well, I'm going to have a fraction here. I have x, but it starts with an x to the first power, and my index is starting at 0, so let me increase that by 1. I have a 1 times 10 in the first term, a 2 times, a 3 times, then a 4, and so again that's an n plus 1, and then I have a 10 to a power, 10 to the n plus 1. 10 to the first, 10 to the second, 10 to the third, etc. Alright, so that takes care of all the terms of the series, and now I have the constant, the natural log of 10. So there is a power series representation of natural log of x plus 10. Let's look at a slightly different exercise here. We want to evaluate the integral of t over 1 plus t cubed dt as a power series and state the radius of convergence. See, some integrals of what we call elementary functions do not have elementary antiderivatives. So sometimes it's necessary to evaluate an integral using a power series. Let's see an example of that. We're asked to evaluate the integral of t over 1 plus t cubed dt as a power series. So what I'm going to do is I'm going to start with t over 1 plus t cubed, and I'm going to see if I can represent that as a power series. Alright, well, t over 1 plus t cubed is t times 1 over 1 minus negative t cubed. So then that's t, sigma, 0 to infinity, of negative t cubed to the n. And using a similar trick as I did in a previous exercise, I can write this as sigma n equals 0 to infinity, negative 1 to the n, t to the 3n plus 1. Let's figure out the radius of convergence of this series, because then upon integration I get the same radius of convergence. So to figure out the radius of convergence, then I would have absolute of negative t cubed is less than 1, and so that implies that the absolute value of t cubed is less than 1, which implies that t is between negative 1 and 1, and so then my radius of convergence is 1. Alright, now let's actually integrate as asked. So then the integral of t over 1 plus t cubed dt. Using a power series representation, I can write that as the integral of, now, negative 1 to the n, t to the 3n plus 1, from n to infinity, would end up being t minus t to the 4th plus t to the 7th minus t to the 10th, etc. dt, antiderivatives, t squared over 2 minus t to the 5th over 5 plus t to the 8th over 8 minus t to the 11th over 11, etc., plus a constant. Put it back in sigma notation. Sigma n equals 0 to infinity. I'd have a negative 1 to the n minus 1. Alright, since I'm starting with a positive, no, I can, that would just be a negative 1 to the n, sorry. I'm starting with a positive, since I'm starting at n equals 0. And then I'd have a t to the 2n, I'm sorry, a t to the 3n plus 2 over 3n plus 2 plus the constant from integration. So the integral of t over 1 plus t cubed dt can be represented with that series, and it has a radius of convergence of 1. That concludes the presentation for this section.